Okay, so far we have looked at vectors. We have seen we have looked at products of vectors. We have looked at also how operators on vectors convert vectors to other vectors. We have also briefly looked at functions of vectors, and we looked at this coordinate transformation, which is a very useful operation in various fields of theoretical chemistry. So now next we are going to talk about differentiation with respect to vectors. Okay, so this is the topic of vector differentiation. And the idea here is the following, that we have seen this is actually differentiation with respect to a vector. So this is with respect to a vector. Okay. So the idea is that if you had a function f of a single variable, then we can define something like d by dx. So this is differentiation with respect to x. Where I mean x is a simple scalar variable, and d by dx is the usual derivative. Now on the other hand, if you had a function of a vector, so we have already looked at functions of vectors, okay, and if you remember, functions of vector are of two types. One are called the scalar fields. So for example, f of x, y, z, and the other are the vector fields. And these are of the type f x of x, y, z, f y of x, y, z, and f z of x. Thus the function itself has three components, and each component is a function of x, y, and z. Okay, so we have two kinds of functions, scalar fields and vector fields. Now we want to look at an operation where instead of differentiating with respect to x, we differentiate with respect to a vector. So we have something like d by d of a vector. Okay. Now it turns out that that there are many ways of doing this. This is many ways, many different derivatives can be defined. And what we will do is we will look at three very popular definitions of these derivatives. Okay. So for the rest of this lecture, I'll be considering the coordinate space x, y, z. So you have functions of x, y, z. So you have scalar functions and you have vector functions. Vector functions will have three components. So this is what I'll be considering for the rest of this lecture. So when I say differentiation with respect to a vector, the vector will be that vector that has components x, y, z. So the vector r, which has components x, y, z. So we'll try to differentiate with respect to r. So wherever we have this d by dv, the object with respect to which we are differentiating is r. Okay. So now if you were just to think out of the box, how you would define a differentiation with respect to r. Now you can say, okay, r has components x, y, and z. So I could do various things. I could differentiate with respect to x. I could differentiate with respect to y. Differentiate with respect to z, and add them. Okay. or do various other combinations. And each of these combinations, and there are three such combinations which are extremely useful, and each of them has a name, and I'll describe them briefly here. So the first one is the gradient. And one more thing I have to say is that now you can take a derivative of either a function like this, a vector field with respect to x, y, z with respect to a vector, or you can take a derivative of a scalar field with respect to this vector. Okay, and so there are a lot of combination of things you can do, and these correspond to various definitions of these vectors, of these vector derivatives. Okay, so the first one we will consider is a gradient, and a gradient is corresponds to differentiation of a scalar field and it is always with respect to a vector, and this gives a vector field. Okay. So what happens in the gradient is that you take a scalar field, you differentiate with respect to r, and you get a vector field. And the definition of the gradient is as following. So the gradient is, the symbol for the gradient is this, and it's usually denoted as a vector, because when you differentiate, when this operates on a scalar field, it gives a vector, okay, and therefore this vector symbol is used on top of the gradient operator. So when this acts on a scalar field, it gives a vector, and the definition of the gradient is the following. This gives you I x So you can differentiate this function. This is a function of many variables of x, y, z. So you can take various partial derivatives, and whenever you take a partial derivative with respect to x, you are keeping y and z fixed. So you are taking a partial derivative of this function of x, y, z with respect to x, keeping y and z fixed. Okay, so I'll write this explicitly. This is partial derivative of f with respect to x, y, and z, keeping y and z fixed. So instead of writing this all these details, I'll just use the short notation here. So partial derivative of f with respect to x, this is partial derivative of f with respect to y, this is f with respect to z, and notice that that the gradient is a vector that points along this direction, okay, along the direction, and these are the three components of the gradient. Okay. So you started with so you took the derivative of a scalar field, and what you got was a vector. Now I'll just mention it briefly here, but I won't. We won't be dealing too much with that. Now here I took a gradient with respect to the r vector. Okay, so this is gradient with respect to the r vector. You can now if your f can be written as a function of Vx, Vy, Vz, okay, and let's make it slightly more complicated. So it can be written both as a function of Vx, Vy, Vz and as a function of x, y, z. Okay. So the value of f at any point depends both on x, y, z and on Vx, Vy, Vz. Now you can define a gradient with respect to, just as you can define the gradient with respect to the r vector. So, okay, so this is gradient with respect to r vector, and this will be defined. This will be defined in this form. So it will be I but you can also define a gradient with respect to the v vector. So if I say v vector, and v vector is just Vx, Vy, Vz. Okay. So how will this be defined? So in this case, notice f is also a function of Vx, Vy, Vz. So the gradient with respect to v vector will be defined as I. Now instead of taking derivative with respect to x, you take derivative with respect to Vx plus j to Vz. So this is the so you can define gradients with respect to any vector, so long as a function as your function is a function of those coordinates, of the coordinates of that vector. Okay. Now for most of the course, when I don't write this r, it is assumed, when I just write a gradient without any vector symbol here, it's assumed that the gradient is with respect to the r vector or whatever which is the arguments of this function. Okay, so let's take a simple example of a gradient. So let's evaluate the gradient. I'll give a function. Suppose I have, so let me do it right here. If I have v of x, this is an example, is equal to, I'll take it as 3xy plus 2yz plus x square plus y square. Okay, so this is a scalar field, it's a function of x, y, z, and now if I take the gradient of this, gradient of v, then this will have I, and the I component is you take the derivative with respect to x. So the first term will give you 3y, second term will give you 0, third term will give you 2x, and the fourth term will give you 0. So you have 3y plus 2x and then plus j. Now in this case the first term will give you 3x, second term will give you 2z, third term will give you 0, fourth term will give you 2y. And the k component, first term will give you 0, second term will give you 2y, third term will give you 0, fourth term will give you 0. Okay. So the various components of the gradient are all functions of y of x, y, and z, and so your gradient is a vector field. And that is what we said. We differentiate a scalar field and we get a vector field. Okay, so that is what is meant. So this is the gradient operation. Now the gradient operation has a very important role in mechanics. Often in mechanics the force is a vector, okay, and this is written as a negative gradient of the potential. Okay. So if you have a type of force called a conservative force, then you can write it as a negative gradient of a potential, and we will look at this example in a little more detail. This is very useful when you are calculating the work done by a force in, let us say, displacing a particle or some such problem. So this is one very important application of gradients, but I mean gradients appear in various other fields also, in thermodynamics, in statistical mechanics, in quantum mechanics. Okay. So you will see a lot of applications of this gradient operator. Okay. So the first type of derivative we had was the gradient operator, and what we said is that it's you differentiate scalar field and get a vector field. So in other words, what you started off was a scalar, and when you differentiate it, you got a vector. So we represented this by gradient operator, and gradient of f of x, y, z j by dou y plus k dou f by dou z. Okay. Now, the next kind of vector derivative that we will see is something called the divergence. And in the divergence, what is done is you differentiate a vector field to get a scalar field. Okay. So here you have a vector field with various components. So if you had a vector field f with various components, z of x, y, z. Okay. Now the divergence of f is denoted as, is written as del dot f. Okay. And it will become very clear why it is denoted in this way. So it is written as del dot f, and the value of this is partial derivative of f with respect to x plus partial or f x with respect to x, f y with respect to y, with respect to z. So you started with a vector and that has 3 components. Now you do the differentiation component wise. The first component you differentiate with respect to x, second component with respect to y, and third component with respect to z. You add them all up and you get a scalar, and this scalar is the divergence. So what you get here is a scalar, it does not have any components, and so the divergence is a scalar. Okay. Now you might ask, why is this notation used here? Okay. In order to see that, we go back to the gradient. Okay. Now when you took gradient of a function, okay, when you took grad of f, you got I dou by dou x of f plus j dou by dou f of y plus k dou by dou z of f. So in other words, you can think of this gradient operator as an operator that looks like this. Sorry, it's an operator. So in the operator form, you write it as in other words, it is an operator that looks like a vector with 3 components. First component is the derivative with respect to x, second component is derivative with respect to y, and the third component is derivative with respect to z. Okay. And when this acts on an f, then you just put the f here. Okay. So if it's acting on f, you just put the f there. Now on the other hand, if you dot it to some vector field like this, what that means is, you can imagine that you take this and you dot it into f, which has 3 components, f x, f y, and f z, and so you have 2 vectors. So just this has 3 components. So you imagine as though you are dotting these 2 vectors. You are taking a dot product of del dot f in this particular direction. And what that looks like, if you are doing a dot product, you would get exactly df by dx and d by dy operated on y, fy, and d by dz operated on fz. Okay. So therefore this notation is consistent with the idea of this dot product. However, you should know that this is not actually a dot product, because dot product by definition should be commutative, and which is not the case in this case. Okay. So it's not a dot product, but this symbol is used, and it is used because it's fairly it's a very short notation and it's very convenient. Okay. So this is the divergence, and and the third definition. So in the divergence, you differentiate a vector field and you get a scalar field. Okay. The next derivative that we will do is something called a curl. So, in a curl you differentiate a vector field to get another vector field. Okay. And I mean there are many ways to do this, but the definition of the curl, the symbol used is del cross f. So, you have a vector field f and the curl operator is written as though you cross it with the del operator, with the gradient operator, and this has and the reason for this symbol will become obvious, because the curl is defined as having components I do z . Okay. So, so in this case you took the derivative of the x component with respect to x, the y component with respect to y, and the z component with respect to z. Okay. But in this case what you are going to do is you are going to take the derivative of the x component with respect to a z here and with respect to y. You do not take the derivative of the x component with respect to x. Okay. And so if you think of these two vectors, then it looks as though you are taking the cross product, the usual cross product of these two vectors. Okay. So, therefore, this is the symbol that is used. Okay. So, each of these derivatives plays a role in various areas. The gradient is probably the derivative that you will see most often in both quantum chemistry and in classical mechanics, because this is related to the potential theory, the force and potential theory. The divergence, you have probably seen it in your courses on electricity and magnetism, okay, but it also appears in something called the continuity equation in hydrodynamics, and the curl is an operator that is probably not as, it's not, you probably don't see it as often, but it does appear in electricity and magnetism, and in general when you're talking about the effect of magnetic fields on molecular systems. Okay. So, we have seen these three kinds of definitions, and the next thing we want to do is to get some sort of way of understanding what is the significance of each of these. Okay. Before we do that, let me take some examples, and I will take an example of the divergence. So, this is an example of divergence. Suppose you have A of x, y, z. This has three components. So, the first component is x, y, z, x into y into z. The second component is x square minus z square, and the third component is x z. Okay, so this is an example of a vector field where each of the components are functions of x, y, z, and if you take the divergence of this field, okay, that means you take the derivative of this with respect to x, that will give you y z, plus the derivative of this with respect to y, that will give me 0, plus the derivative of this with respect to z, that will give me x. So, this is a divergence. Okay, so, the divergence is fairly straightforward to calculate, and the curl is also straightforward to calculate, only you have to take a few more derivatives here. So, the curl is a vector. The ith component involves differentiation of the z component with respect to y, which gives me 0, and then differentiation of the y component with respect to z. So, that will give me minus 2 z. So, this is 2 z y, 2 z I plus j. The j component will involve derivative with respect to x of the z component, that will give me z minus x y, and the kth component will give me 0 oh no, kth component will give me 2 x here, and it will give me minus the x z. Okay. So, that is the curl of this vector. So, you should be able to calculate the divergence and curl for any vector field, just as you should be able to calculate the gradient for any scalar field. Okay. So, these are relatively easy to calculate, and it's expected that you should be able to do all these calculations. Okay. So, let us look at the physical significance of each of these quantities. Okay. So, we have the gradient, divergence and curl, and let us look at the physical significance of each of these, starting with the gradient. Okay. And here I won't give the full explanation. I'll just briefly explain, and you can look up one of the textbooks or references to find out to get a better understanding of this.